gamma inside the for finite completion. They exist unfinitely, some finite set. S, where Zx is just inverting the S, and this is always the case because gamma is finitely generated, so the denominators of the matrix of gamma belongs to have factors among only involving finite many primes. And then the statement is that then the image of gamma is dense. The closure of the image of gamma is open in the for finite completion. Sorry, in the congruence completion. And here this is the congruence closure. And of course, another way to state it is that accepting some finite set of primes, maybe by enlarging S if you like, then any congruence image of this group is also a congruence image of this group. Okay. Now this is actually the reason I stated this is actually a theorem which was proved independently by Nori and also Weisweiler. Independently. I think this was actually Matthews and Weisweiler. Now, the proof by Matthews and Weisweiler uses the classification of finite simple groups. Nori's proof is algebraic, and they also had a proof. For example, there's a proof by Khrushchevsky and Pillay using logic. Now, I want to simplify things. So from now on, let's just simplify. So I'm going to give you basically the Nori's proof, and already the main ideas you can see in the simplest possible case. So from now on, let's take G to be just SLN, and gamma sits inside SLN Z. Z is dense. Right? You're going to see all the ideas already there.
Now, SL2 you don't see all of the ideas. SL2 is simpler.
Probably for SL2 you already see it, but the proof I have in mind doesn't really distinguish very much.
SL2 basically all the subgroups are essentially solvable, so it's easier.
Okay. Yeah, probably doesn't matter. But so what we have to show? We have to show that. So what is the congruence completion? In that case, I can take S to be the empty set of primes. So and then the congruence completion. By the Chinese remainder theorem in this case, which in general is a form of the strong approximation theorem for this arithmetic group. This is a product of the congruence completions of various primes. Okay. And now let's so suffices to prove. Let's just say suffices to prove first that the image of the projection of P of gamma into SL and ZP has open closure for each P, and it's dense at the same projection. Actually is dense And I claim this is enough. Why? Because now if you have now if you have a general congruence quotient here, so we're talking about something like SLN over Z mod P I to the power Ki of Z. Product for finitely many, yeah. I from 1 to m, say. This is a general congruence quotient now. I claim that it's sufficient to prove that the projection of my gamma satisfies these properties on each of these factors. And the reason is that these factors don't share they don't share composition factors among themselves. So if I take Pi bigger than so bigger than 3, then these groups, this collection of finite groups and have no common composition factors. I like it because there's also a C cyclic group inside here. So, if you look at the first congruence quotient, yeah, this is almost a simple group, yeah. So it's a simple modular center, and it's different from all the others. So different primes, you get these are the groups PSL2s are as different and simple. Simple. Why are they different? The easiest way to see is probably look at the Silo subgroups. So at the prime Pi, this group has a very large Pi Silo subgroup, namely the upper triangular matrices. Yeah. Whereas for different prime, the Pi Silo subgroup will be quite small. It will be practically almost a subgroup of the diagonal matrices. So this one way to easily see that there is no isomorphism between these groups. Okay. And of course, below them, once you pass the first congruence quotient, the other composition factors are just P groups for different primes. So they're different. So the moment you project onto all of these factors, you're okay. Right. Then you get actually, the moment my group projects onto all of these factors, because being dense just says there's a gamma maps onto this one. Yeah. Right. Now, the good thing is we also actually proved this one. This one I gave you a proof in my first lecture, and the reason is because the closure of gamma here is an analytic subgroup, and we proved that by the risky one point where we use that it's a risky dense, we proved that its Lie algebra is actually an ideal of the Lie algebra of SLN ZP, which is little SLN ZP, which is a simple algebra, has no ideals. So therefore the ideal is everything. So then this is a full subgroup. If it has the same Lie algebra, then it's an open subgroup. But of course, the main thing is here. And now, so it's sufficient to prove. Next step. To prove that now let me call it pi p for almost all prime p. the phi p, the map from gamma onto SLN FP, that's the map mod P, yeah? Is surjective. Now, why is that? That is because, now let's look at one of these groups. Now, C is fixed, and I want to hit, for almost all primes, I want to show that my gamma projects onto the whole of this group. Right. So let's say I have let's call delta to be the image of gamma under this projection. So delta is the image of gamma modulo p to the k, right? And the claim here is that the Frattini subgroup here, the Frattini subgroup of SLN Z mod p to the kz, is actually contains the first congruent subgroup, the kernel of the projection mod p. How do we note it? SLN1.
Can you remind us what the Frattini subgroup is?
The intersection of all the maximal maximal subgroups. So, okay, the Frattini subgroup of a group is the intersection of all M, such that M is a maximal proper subgroup of G.
Okay. Okay.
It's a finite group.
My group is finite. Yeah, in the case of finite groups, you have to take closed, which is the same as open. What is the property of the Frattini? Okay, it says that a set generates. So equivalent, you can define it as saying that this is the smallest group with the property that if S generates G mod the Frattini, then it already generates G. Right? Somehow, if you can generate it more than that group, you're done. So I want to show that the Frattini contains the kernel of the so this is just the matrices were congruent to one mod P. In other words, I want to show now that if delta maps onto SLN FP, then delta is gone. Then delta is 0. Okay. Okay, so what are we going to do? We're going to, okay, let's start induction on P. Case equal to K1 is trivial. Yeah. Let's, the key thing is to do the case K equal to 2.
So what are you assuming now? What are you trying to show and what are you assuming?
So this to prove. That's what I want. But if a subgroup in this finite group maps onto the first layer, then actually it's everything.
What are you assuming? What are you assuming?
What am I assuming? Well, I'm assuming that, well, I think I want to assume that P is slightly bigger, so maybe for P bigger than N, just to be on the safe side.
But what's the assumption on gamma? I lost where you are as a proof.
Assumption? Delta is the image of gamma.
You have something to SLN Z mod 3K, and you assume it is factor onto the NFP.
Yeah, maybe you know the
Prove that this is the whole thing.
I have a subgroup of SLN of the matrices modulo P to the K, and if it maps on all matrices mod P, then actually it's the whole group. Now this is finite group theory, and it's, let's spend 5 minutes here. Why is that? Let's first prove it for K equal 2. this would be the key case. Right? Because suppose this is not true. Suppose that delta is actually not everything. But then let me call V to be basically the SL n 1 mod Z times P squared. Z, yeah? In fact, this is these are the matrices which are congruent to the identity mod P, and they take a modulo P squared. Yeah. So Moment's thought shows that this is actually 1 plus SL n at P. Oh, does this make sense?
What is L?
It's what? Maybe GLF.
These are the matrices of 3, 0. Yeah.
Only
Is little L up there?
I have an extra L.
Or the SLN, what is this? Left.
Yeah.
On the other side of the
This is
equality.
1. Ah,
No,
the identity.
other side of the equality side.
Yeah.
What is this superscript?
Ah, these are the matrices congruent to 1 mod P. That's what I'm trying to.
Oh.
Alright, maybe I should describe it, but just be more precise. This is the identity. Plus entries P Aij. Yeah. Yeah. Where Aij is in Z mod P. So each entry is each entry of the diagonal is congruent to P mod P squared. Yeah. Now, this B, this is a normal subgroup. In fact, it's an abelian group, as you can see. As an abelian group, it's isomorphic to this. Yeah. So V is isomorphic to SL, the Lie algebra under addition as an abelian group. It has dimension n squared minus 1. And also this describes the conjugation action of the first layer on the second. Yeah? And with the standard action, with the conjugation action of SLN LP on. And the conjugation action is the usual action of conjugating matrices. Yeah. But then this is basically this is irreducible. V is irreducible. Module for SLNFP. Right? Well, that's standard. There's no subspace of these matrices which is invariant under conjugation. So it's U. Yeah. And so now if delta was not everything, then basically delta must intersect. This thing is invariant under conjugation. Because certainly delta V is the whole group, yeah, it's the whole group. And therefore this is invariant under conjugation both by delta and by V, certainly by V because V is abelian, so it's a normal subgroup. it's invariant under the whole group by conjugation, but there's nothing invariant except 0 or v. So this cannot be 0 because otherwise delta will contain v and therefore the whole group will be 0, so therefore this must be 0. So now delta intersect v or in the identity theorem. And the group notation is correct. But now I claim this is not possible because if I take a matrix here, now this is now just a computation. Take the matrix which looks G, which is in delta, which looks like 1, 1, 1, 1, 1, and congruent to 1 mod P. Yeah, so congruent to E 1, 2.
Now you prove that this extension not split, right?
Yeah, I'm proving that this cannot split. Yeah, and it's really very simple because if you take a matrix which is unipotent E1, 2 in Near's notation, the matrix which is just 1 just off the diagonal. Yeah. In this group, you just compute that A to the P cannot be 1. In fact, A to the P is actually always must be congruent to is congruent to the matrix which looks like 1, 1, 1, 1, 1, and P here. And then some junk here. But this is mod P squared. Yeah. So this of course lies in V, but it's not 0 in V. Yeah. The zeros in V are those which are zeros mod P squared.
Can you repeat one step before what you said here?
Right. So if my the whole group, let's call this group H. Right? Mod the matrix is mod P squared. So we have that H is delta times V, because I'm assuming that delta projects modulo V. Yeah? And V is abelian. But then, in that case, the intersection is a normal subgroup. Yeah. So it's invariant under the action of the top group, yeah, under SL and FP. But this is an irreducible module for the SL and FP. So the only invariant subgroups here are either 0 or V. But so if this is V, then delta contains already V, so delta is equal to H, which is I want to prove. So the only possibility is that delta intersects V at the identity. So this is a split extension. But then if I now this A, right? This A corresponds to the matrix 1, 1, 1, 1, 1, 0, 0, 0 in SL and FP, right? And this is isomorphic to delta after all. Yeah? Delta is isomorphic to the quotient. Yeah? Now in SL and FP, this matrix has order P.
What is A now?
Hmm?
What is A?
A is this matrix.
Some element congruent to this.
And what does it have to do with G and delta?
Hmm?
What does it have to do with G and delta?
Maybe you can
This is G. Yeah.
conclude by the fact that the semi-direct product doesn't have an element for the P squared.
Well, yes.
IP is an isomorphism.
Yeah.
It's kind of-
Yes, the elements of order P on in the top group look like that, yeah. But I really want to use just a single elementary matrix. So, see, I mean, if this was true, then delta will be isomorphic to SL and FP via its projection. So then I'm taking an element in delta which corresponds under the projection mod P corresponds to the matrix just E1, 2. And I know that it must have order P. Because this matrix in SL and FP has order P. And delta is isomorphic. But if I raise it to the p power, this is a non-trivial computation, by the way. It's because it's you also write. I mean, A is this matrix plus p times x, where x is from right below. So you have to raise to the p power, but x and a may not commute, so you have to do some computation. Yeah, and this is not the identity. Another way to say that this somehow it ended both in delta and in V, and it's not the identity. Right. So, but now, once we get that, now we know that delta maps onto the matrices mod p squared. But then after that it's easy, because I will take a matrix which is of the, say, let's take the matrix now, this matrix mod p. Yeah. Now take something g in delta, and g is congruent to this mod p squared. But then if I raise it to the power p, this will become congruent to 1 p squared mod p cubed. Right? This is now. Yeah. Here I'm just using the identity that 1 plus alpha to the p is congruent to 1 plus alpha to the p. Well, alpha, my alpha is important. So this is congruent to this model. In fact, even better. If I have something like identity plus p times the matrix, if you expand this, basically you're going to get that this is congruent to 1 plus p squared now. So then we're getting all the layers one after another. Basically, after the zeroth layer, which is a problematic one, the first one maps directly onto the second one by the p power map. Yeah. So this is an example of a uniform group. So this is another the general fact is that the group ZP is uniform. The first column. The moment you get the top one, you're done. Right, and of course this is the key thing. This is what we want. So, it remains to prove that gamma, my Zariski dense group, maps onto SLNFP for all large primes. And the only thing I know, it is the Zariski dense. So let H again be the image. And now there are two things we have to prove about it. The first thing we need to prove is that H has elements of order P. Let's prove that. If that is not the case, if not, then of course P does not divide the size of H. Silow's theorem, Cauchy's theorem. And so, this H is a linear group in cross characteristic and then we can apply Jordan's theorem. So Jordan's theorem looks for finite subgroups inside SLN-C, but the original proof of Jordan actually shows that doesn't need C. It's completely algebraic and just needs the characteristic of the field is different. So here is a Jordan statement. If H is a subgroup of GLN K, where the characteristic of K does not divide the size of H, then H has an abelian subgroup of index at most f of n, yeah? Where f is a function only on n. Okay. Right, so if this was false for all primes, for infinitely many primes, suppose for infinitely many primes this was false. So then we have infinitely many primes where the image of we have an infinite collection of primes P1 into Pi such that the projection mod P of gamma inside SLN FPI, the mod P projection is basically bound is abelian by extended by bounded subgroup, bounded size. Right? But then now my group is also residually in this class. So gamma is residually in SLN FPI. Yeah, that's because the intersection of the kernels of SLN Z into SLN FPI is for infinite set of primes is just the identity, right? There's no matrix which is congruent to 1 modulo infinitely many primes unless it's the identity. Yeah. So my gamma is residually in this class, and it's kind of abelian by bounded size, but gamma is finitely generated. So again, by passing to a sufficiently deep subgroup of index which kind of is bigger than this bounded size, normal, then I deduce that gamma is virtually abelian. Abelian, but this cannot happen because gamma is a risky dense in SLN. So we have done, we prove this. There are elements of all of it. And here's a second statement that we need. We need to fully exploit the fact that gamma is a risky dense. So here's what I want to conclude. So for sufficiently large claim, for large P, depending on gamma, the Lie algebra of SLNP, which is SLNFP, is irreducible as H model. So again, H acts by conjugation because H is a subgroup of H is the image, right? H is a subgroup of SLNFP, and that acts by conjugation on traceless matrices. Yeah, and I claim that the H action is irreducible. Well, why is that? Well, because gamma is a risky dense. So if I look at the action of now I have the action of SLN Q. Okay, SLN Q. Q acting on SLN Q is irreducible. but because gamma is a risky dense in SLNZ, gives me that these two groups have the same span in the so basically they have both have the same Q span. Have the same Q span inside all the endomorphisms, all the linear maps of SLN as Rash, also just as linear maps. Yeah. The conjugation, so both have the same Q span as conjugation from conjugation. So the conjugation action of the group SLN induces certain vector, if I take the span of it, that induces some linear subspace here. The conjugation action of gamma also induces some subspace. And I claim that they must be the same spaces because otherwise I can separate them with a linear functional, but that will contradict the Zariski density of gamma inside SLN. Yeah. There will be an equation. I think these are polynomial actions after all. So I think that I already used that earlier. Okay, but if they have the same Q span, then of course if one is irreducible, then the other one is irreducible. Yeah, that's clear. And now because they're given by certain, now if I replace Q with Z, and I look at the matrix generators of the matrices of gamma, I have some collection of matrices, some finite collection of matrices will give me the same span here. But then I look at primes which avoid the denominators of the coordinates of these matrices, and I can just reduce the entries mod P and reduce the same condition for infinitely many primes. Yeah, this is standard argument. If a bunch of vectors with integer coordinate, with rational coordinates generates Q to the n, then I can avoid finitely many primes and reduce the entries and still know that they will generate Fp to the n. Yeah. So then I can say that for almost all primes, P, they have the same Fp span. But then again, because the second group is actually reducibly there, then the H1, then H also acts reducibly. Yeah. So this basically proves this. Yeah. That's linear algebra basically. Yeah. At one stage we need the Zariski density to reduce the two vector spaces of the same. Right. Okay.
Would you say the same as FP span like SLN Z or SLN Q somehow? I don't. What exactly are you saying here?
Well, I started with rational. Well, in fact, so wait. Okay. Actually, I don't need here. I can just keep gamma. Sorry, I can keep here, and then I just act I just act by SLNZ and by gamma on the Lie algebra SLNQ, and take the span of these two groups. I don't need to pass to Q here. Here comes now the noise. Nori now uses only this. well, we prove something more general. But from now on, let's say the NOR is simplified, kind of weakened, like weak NOR, that is actually going to be good enough for us. Is saying that under these conditions, that now we have a subgroup of SLNFP. We know that H has all elements of order P. And we know that basically the algebra is irreducible. Is H irreducible? Then, provided P is big enough, but only compared to N. Now we can. This does not depend on H anymore. Provided P is big enough compared to N, then gamma H is equal to the whole. And that will do it. That's what we want. Now this is the weak NORI, which we're going to prove. The strong NORI that is in is much stronger, and it says the following. You can actually realize if H has elements of order P, let's put H plus to be the subgroup of elements of H which are generated by a subgroup of H which is generated by elements of order P. Yeah? And then he realizes this as the FP points of an algebraic group. So he takes now. Now, if you have an important element, so if you have an element of order P, you can take now look in GL and FP, and then I can start exponentiating my G in the following way for any T. In FP, well, so basically, yeah, so in FP bar, I can make sense of G to the. So, yeah, I can define this one parameter unipotent subgroup. That's what I want to say. And one way to define it is you can basically take log of it, and then you multiply by t, and then you take x per it. Right? And the point being that log and x makes sense because log of g is by definition is basically the sum of g minus 1 or 1 minus g to the power s divided by s factorial, but you don't have to do it for many s's. You can do it from 0 to n minus 1. Yeah?
Probably not s factorial.
Not s factorial for log, yeah, that's it. So here we're assuming now that p is bigger than n. Yeah? So these denominators make sense, and we don't have to go further because this is a nilpotent matrix if I raise to the n power that.
So what are you doing now? Are you now proving the weak one? Or
No, I want to say what is a strong one.
Okay.
So, okay, are you happy with one parameter subgroup change by G to T?
No,
Yeah. So this is the log map. We can define it on the set of unipotent elements, and on the set of new. Notice that this guy is now nilpotent. Right. But then on nilpotent elements, I have X map, which is the what it should be, right? So. Now I have if the matrix A is nilpotent, then I can define. Then of course A to the n will be 0. I don't have to go. And then I can define x of a as the sum of a to the s divided by factorial s from 1 up to n minus 1. And now I here realize I've forgotten the sign. There's some alternation of sign, like plus minus 1 to the power of sign. Yes, log changes. Right. And again, this makes sense, and you don't have to go further with this. And then these are established by ejection between the unipotent and nilpotent elements. So it's trying to resemble the Lie algebra, but of course.
You don't need the change of sign because it took 1 minus 2.
Really?
This is 3 minus 1 you need.
Right. So then this is an algebraic subgroup in GLM. This is a one-parameter algebraic subgroup. Yeah. Imagine what is happening is I have a unipotent matrix which looks 1, 1, 1, and it has a single entry here, which is some alpha in FP, and then I'm taking the algebraic closed field and I'm just multiplying it by t. Raising to the t power is multiplying it by t. Yeah. And t now is the element in the algebraic closure. Okay. And now, this is the one parameter subgroup. Call this guy xt, xg is the one parameter subgroup of t a. This is a one parameter subgroup. Xg is isomorphic as an algebraic group to the additive group of the G plus, yeah. The additive group of the field. Yeah. So it's connected, and we put G tilde. The algebraic group generated by all these xg's for G nilpotent, G order P in H. Yeah. This is a connected algebraic group in characteristic P. And Norris strong theorem, strong Norris, the real Norris, is that this H plus is equal to the rational points of this G tilde. So he realized the group generated by P elements as a rational point of an algebraic group. And now, why is this much stronger? Well, because here the only possibility for G tilde is to be SLN. It's easy to see that under these strong conditions, G tilde is an algebraic subgroup, but this must be, you quickly realize this must be the Lie algebra of G tilde, so G tilde must be the whole. And you can even further get a control on the quotient H mod H prime by the version of the Jordan's theorem. H mod H plus is basically virtually a billion. Now the proof is actually also not. It's very starts very elementary of this. It establishes a bijection between unipotently generated groups and unipotently generated Lie algebras. It just uses linear algebra and a little bit of schemes and stuff like that. But because I don't know schemes, I'll just try to do this. And for this, we don't need schemes. 5 minutes. I think I can do this. Right. This. So, what is the idea? Well, we start as in Nori, right? We take the H prime, we take the unipotent elements, and look at the collection of logs of the unipotent elements. We look at this collection and call this set L. What is amazing is already it turns out that this is a Lie algebra over FP. Nori proves, by the way, this, which is just a set. No, he proves that the F span of this. So let's call this the F span of this set, the linear combinations of these matrices, This is a subset of the matrix group of matrices A and T. Right? In fact, inside these are traceless matrices, as is clear because these are important. These are traceless matrices. And Nori proves that actually we have obtained a Lie algebra, but we don't need it. Why? Because the only thing we need is that this is automatically H invariant. Yeah, by this definition, the set of elements for the P is invariant under conjugation, so are their logs, they're polynomially defined. But then, therefore, L must be everything. This L must be everything. And therefore, from this base, so this is a spanning set, I can select finitely many elements. So now I can choose G1, G2, G M, where of course M is a dimension, M is n squared minus 1, which whose logs span all the traceless matrices over P. Yeah? And they're from H. Yeah, that's nice. Good. But then now, just consider the following set. A is the following set. I just consider some kind of a big chunk of the group will be given by just raising them to power T1, T2, Gm to the power Tm, where these Ti's are in Fp. Let A be this set. And now observe that raising the matrix to the power of a field element is actually a polynomial map. Because I just wrote you what it is, and each of these is a polynomial map, so of degree up to n. So this guy is an image of some morphism of algebraic groups from Fp to the power m to my SL NFP, which is also of dimension FP of dimension m. Yeah.
Morphism of the values.
Yeah.
Morphism of spaces.
Of morphism of algebraic varieties. And now the derivative of this map is basically the derivative in the formal sense of these maps is exactly log the derivative of g to the t. T goes to g to the t is basically log of g, the tangent. Yeah? So because these guys span the whole of the tangent space of this algebraic group, I can write a certain Jacobian. Now this becomes algebraic geometry. There is a certain Jacobian in t squared variables, which at 0 is not 0. So this is some polynomial, which is very kind of even though it depends on g, its degree does not depend. Its degree is bounded by a function of n, because you're just taking the coordinates of these maps, which are bounded degree, taking their partial derivatives, taking a matrix, and it doesn't vanish, right? So basically, the j at the 0 point is well, yeah. It's not 0. That's the only thing. Okay, and then what we do, we take, say it's 1, you can always normalize it if you want. And then take the pre-image of the, let U, now this is standard algebraic geometry, take the inverse, the the preimage of 1. Oh, no, I need the open set, sorry. I need the open set. So I need all the tuples in A such that J of these tuples is not 0. So this is an open set.
The T's?
These are tuples. I'm talking about the excesses. Yeah. I take the open set where the Jacobian does not vanish.
So you mean you take this G1 to the T1 where...
Yeah, X1. Yeah. Also, so yes. Oh no. I see. Mistake. X in FP to the power m. Thank you very much. Yes. Take all these powers where the Jacobian does not vanish, and then restricting to what is the size of this set? This is like actually a fairly big set. Yeah, it's an open set, so it's clear that the size of U is bounded from above is at least something like 1 minus O of 1 over P. No, I want to say it's bigger than the whole thing minus capital O of P of m minus 1. Yeah? Right? Because when the Jacobian vanishes, is a proper subvariety and it has at most constant times, the degree of the Jacobian times P to the m minus 1 points by obvious estimates. So it's a fairly big set. But then on U, this map, which I didn't give you a name, the map which sends x to the product of gi to the xi has basically finite fibers of bounded size. Because this is an example of a Tal morphism, a magic part. And as Nir told me, it's a consequence of Bezoos theorem. Right, and this D involves it depends only on the degrees of this morphism, which is again bounded by a function of n. So this is controlled by a function of n. But if the fibers have a bounded size, then this means that the image, the size of A is fairly big. Yeah, then it's bigger than basically P to the m divided by D times something very small. O of 1 over D. Okay. And of course, this is of course at least H. H is at least that big. Right. On the other hand, SLN FP, now this is kind of the home stretch, is basically less than P plus 1 to the power m. Yeah, m is n squared minus 1. It's not exactly p to the n squared minus 1, but certainly p plus 1. The m does it. And so the conclusion is that this has index at least at most p here. Right, so the ratio of H divided by A is at most this is bigger group. I won't say this is less than P.
SLFP mod H.
Oh yes.
Now just there aren't such something because you assume that n is greater than p.
So index p plus 1.
Yeah. So yeah, for big enough, for P large enough. But now, here's the simple fact. What Mark is saying is that since any SLN FP is generated by elements of order P, by elementary matrices of order P, So has no subgroups. So has no subgroups of index less than p. Yeah? So if a group is generated by elements of p elements for p, it cannot have subgroups of index p. So basically these two are the same. Which is what we needed. I mean, this was enough for us. Yeah, and as I said, nobody proves much more. And maybe I should conclude that. So what I gave you is the result is called strong approximation for the risky dense subgroups. Yes, but there is even a better results nowadays. So there is some results which can be called super strong approximations because, of course, probably many of you know about this. Once I have this the risky dense subgroup and I know that gamma maps onto SLM delta P, says the risky dense in a simple connected Lie group, then I can say, but then look at the Cayley graph here, and what I just proved is that this Cayley graph is connected. But then the next question is like, is it well connected? Is it an expander? And the answer is yes. On the based on the work of many people, Green, Tau, Bourgain, Gamburt, and Bieber, Szabo. There is a theorem by finally the one I want to mention is by Golsipidi, Salehi Golsipidi, and Pariu, which actually shows that there exists some epsilon such that images of gamma. So gamma is finally generated the risky dense in SLM, FP of R expanders. So if I fix the generating set for S with respect to a fixed generating set. So in fact, there are even better versions because one can also take not just the images modulo primes, but products of primes, square free numbers. So actually, I'm not sure if they got all the prime powers now, but probably they have. So this
Epsilon depends on gamma.
yes. And involves many techniques which they start actually with Nori and proof, and it becomes this is the next generation proof. Very they involve both algebraic geometry, some combinatorics, and yeah, it's a subject for different course, but it's kind of obviously the continuation of this. Thank you very much.
You finished your course? Or?
Yeah.
Thanks, Nick, for a really wonderful course. So you gave much more detail than in your lecture notes.
That's right. Now I know more.
Okay, so it's more than we expected.
So is the strong Nori necessary to prove it for other algebraic proofs? That's the point?
No, the same proof actually works. In this case, what
Give
you
a classification of how the finite subgroups look like.
Yeah.
yes, but I mean, for any given G, the P will depend on how big P has to be will also depend on G, but this can be adapted to any.
But there is an issue when you're talking about extensions of SP, right? About bigger feet, or there's no issue?
But there's no issue because for given gamma,
I mean, there is some work of Larsen and things, right? Which is somehow relevant.
yeah, this could be extended to fields which are bigger, which are of unbounded degree over P. But the fact is that if you have a given gamma and you put it once inside an algebraic group, and basically that determines your field extension, and then that's fixed. So actually here you can put some extensions, but they're all bounded, so you can put them in the degree immediately. So it's okay. Just this is okay. I simplify it greatly because I assume that the group G is SLN, but it can be much more complicated.
Do you want me to revise the vice failure? Result vice failure.
No, that uses a classification. But this was known actually. This people knew that. So this argument you can find in the papers of Tao. This is not my understanding. I mean, it is in Norris' arguments after all. It is just it's kind of written in a very. There are lots of schemes at some stage, and it's scary. But ultimately, that's what we need only. So it's understandable.
But does Nori use this Fratini argument?
The Fratini thing is standard.
Yeah.
He only stops at SLNFP. His original paper just works in SLNFP. And then he makes a remark that I've become aware that these results can also be used to prove results about congruence images. And this will come in the following paper, and somehow he never actually writes this following paper.